This is the fifth week of this week, fifth class of this week. You see, in the last class, we demonstrated how array stress function can be used to solve elasticity problem in Cartesian coordinate system. We will be doing the similar exercise, but in polar coordinate system. We will just write down the equations in polar coordinate system today, and the next class we will demonstrate those equations through few examples. Okay, so today array stress function in polar coordinate system. Now, if you recall, in cylindrical coordinate system, these are the components of stresses. We have three directions which are r direction in a radial direction, then in a theta direction, and then along z direction, and these are the different components of stresses in different directions. Irrespective of the coordinate system we choose, the governing equation, the del dot sigma plus b body force is equal to 0, that will remain same. Depending on the coordinate system we choose, the expression of del and expression of and the components of stresses and component of b will be different. Now, if we substitute this component of sigma and corresponding component of del, then this is the governing equation in cylindrical coordinate system. We derived it in previous classes, one of the previous classes, where BR, B theta and BZ are the body forces in different direction, R, theta and Z directions. Now, in order to get the polar coordinate system, what we have to do is we have just polar coordinate system means then the problem is a plane problem. So, the direction z direction, we have to remove this z direction. So, all the components of stresses that we have in z direction, that will vanish. So, this will be we won't be having this component, we won't be having this component, and the entire equation will not have, because now that particular direction does not exist. So, then if I have to get the corresponding equation in polar coordinate system, then the equation becomes this is the polar coordinate system, and the components, these are the component of stresses. Now, at this point, these are the component of stresses which are independent, because depending on plane stress or plane strain problem, we may have stress in z direction or may not have stress in z direction, but that stress for plane strain problem, we may have stress in z direction, but that stress may be obtained by the other component of stresses. So, these are three independent stress components. Now, corresponding equation becomes this, all the terms associated to z direction, now there straight away we can remove them. So, this is the governing equation in polar coordinate system. Now, next is strain components. Now, similarly, these are the three strain components, sigma r, epsilon r, epsilon theta theta and epsilon r theta. Again, depending on whether it is plane strain or plane stress problem, we may have strain in the z direction. For instance, for plane stress problem, we can have strain in z direction, but in that case, that strain component can be obtained by the other strain components. Now, again, irrespective of the definition, irrespective of the coordinate system, this definition of this relation will remain same. This is the strain displacement relation. These are the gradient of displacement field. Now, if I express this relation in polar coordinate system, then we have these are the three different strain components. Okay. Now, epsilon r, epsilon z, epsilon theta theta and epsilon z r theta. It is epsilon r, epsilon theta theta and epsilon r theta. Okay. Now, next is, so we have the stress components, we have strain components, we also have the governing equations in polar coordinate system. The next is, let us see what are the different what are the stress strain relation in plane in different formulation, plane strain and plane stress formulation. If you recall, this is the relation between stress and strain. So, sigma r becomes, in this case, if you recall, here sigma r is equal to, or for instance, let us write down the expression here, we also have the expression. So, this is the expression for sigma ij. stress component as a function of strain. Now, suppose if we want to find out strain in sigma r in r direction, so sigma r will be similarly lambda into epsilon r plus epsilon theta and then plus 2 mu epsilon r. So, this will be the sigma r component. Similarly, we can substitute r and theta in place of I and j, we get other stress components as well. Then similarly, strain is this. So, similarly, if we have to get the, say for instance, strain in epsilon r, it will be 1 by E into sigma r minus nu into sigma theta. Similarly, we can substitute different components in place of I and j, we get the other strain components as well. Now, if we do that, so these will be the different stress and stress components in plane strain. Please recall, this has been discussed many times, but again for plane stress problem, the stresses in a particular direction is 0, all these stresses are 0, and for plane strain problem, strain in particular direction, all the strain along z direction is equal to 0, but it does not mean that all the stresses will be 0. We may have stresses, we may have sigma z as a function of sigma r and sigma theta. Similarly, for plane stress problem, the stresses, all the component of stresses in z direction is equal to 0, but it does not mean that strains are also 0. We can have epsilon z, but that epsilon z can be obtained by knowing epsilon r and epsilon theta. Please note that it is whenever it is written epsilon theta, it essentially means epsilon theta and epsilon r means epsilon r. Okay, that is the notation we use. Okay. So, we now know what is the stress strain relation for stress strain relation in polar coordinate system. Now, let us write the other equations. Navier's equation, which is essentially the displacement formulation. So, we write everything in terms of, in the equilibrium equation, we write everything in terms of displacement, and if we do that similar to the Cartesian coordinate system, we do the same exercise, we get the corresponding equations in plane strain and plane stress. This is epsilon in r direction, this is theta direction, r direction and theta direction. Okay. Now, so this is for plane stress and plane strain. As far as the derivation of this concern, it is exactly same as for Cartesian coordinate system. Only difference will be the operator del are now different and the components of stress and strains are different. Rest of the things is just the substitution of the rest of the steps are same. Now, once we have this Navier's equation, then also let us write this governing equation in terms of displacement, which is compatibility equation, and this is the corresponding equation in terms of displacement. Okay. Now, you see again, if the body force is 0, then this part vanishes, then what happens? Your equation becomes del 2 sigma r plus sigma theta, that is equal to 0. It is again exactly same as Cartesian coordinate system. Okay. And for plane strain and plane strains, both are same. Next, so we have written the equations in terms of stresses, and let us now see how to solve these equations. Okay. Please note that there are many solution methodology, but the solution methodology that we have been discussing in this course is stress based formulation and solution by power series method. There what we did is we combined all these relations, we define a potential was a stress function, Airy stress function, and which the Airy stress functions are defined in such a way that the governing equations are automatically satisfied, and then the rest is the compatibility equation. Then we substitute all these definition, all these expression for Airy stress function in the compatibility equation and get the biharmonic equation. That is what we did it in Cartesian coordinate system, and we will be doing that same thing exactly for polar coordinate system as well. Now, these are the definition of Airy stress function. Phi is the Airy stress function, and this Arrhenius stress function is related to different components of stresses like this. Now, once you can do that exercise, you substitute this all this component of stresses in the equilibrium equation and then check whether the equilibrium equations are satisfied or not. As the problem generally we have been considering, there is no body force, that is why in this definition of Arrhenius stress function the body force term is not included. But if you have body force term in your formulation, then you have to include that body force term in this definition. Now, once we have Arrhenius stress function, then the rest is we have to substitute this. You recall this is the compatibility equation, this is the now in that expression we have to substitute sigma r and sigma theta, and if you do that, substitute that this definition of sigma r, sigma theta theta and sigma r theta, then we have biharmonic equation like this. Here we assume the body force term is 0. So, which is again essentially del 4 phi is equal to 0. Del 4 phi is equal to 0. Del 4 phi is essentially, if you recall, del 4 phi is del 2 phi is equal to 0, where del 2 operator in Cartesian coordinate system was del 2 del x 2 plus del 2 del y 2, if you recall, but now in polar coordinate system that operator becomes this. Okay. So, if we substitute this operator in this expression, the entire operator in this expression, so we get this. So, this is our final equation. It is the same equation that we had in Cartesian coordinate system, but now the operators are different because the coordinate system is different. Now, the rest is, once we have the governing equation, this is the governing equation, the solution of this equation is phi, which gives us the stress field. So, once we know the stress field via phi, then we have to apply stress strain relation to find out strains. Once we have strain, then apply strain displacement relation to find out displacement, and in the entire process wherever we come across the constant for integration, we have to use different boundary conditions to find out those constants. Okay. That we will be demonstrating through one example shortly. Now, you see, so this is this equation. You recall in the Cartesian coordinate system, what we did is del 4 phi was del 4 phi is 0, even del 4 phi is equal to del 4, right, del 4 phi is equal to 0. We assumed that phi as polynomial, right. Suppose for instance, it is a 0 0 plus a 1 0 x plus a 0 1 y and so on. Okay. So, we assume the phi is a polynomial, and then all the polynomials which are less than third order, the order is less than up to cubic polynomial, that up to cubic polynomial automatically satisfy this equation because this equation is fourth order. But if we have a polynomial which is, so if for a problem where we assume the expression of phi as up to cubic polynomial, we really did not have to explicitly show that if that expression of phi, that assumption of phi satisfies this equation, because it is it satisfies, the order is less than the order in the equation. Now, if we assume phi which is more than third order, then we had to satisfy compatibility this equation, and we substitute phi in that expression, get some relation among this constant, and that relation we can use to find out the along with the boundary conditions to find out the constants. Okay, that is how we apply the Arrhenius stress function in Cartesian coordinate system. Okay, now in here it is just not, you will see here we have r term and theta term, and therefore, unlike the Cartesian coordinate system, here in the expression of phi, we may have some expression of r as a polynomial or some expression of theta as trigonometric function. Let us see that. Now, so this is the general expression of now what we have, we can find out general expression of phi from this equation. How to get that? Suppose you assume that you can apply, we have two coordinates, one is r and theta, and phi is a function of r and theta. We can assume that separation of variable can be applicable, and then we can assume that phi is a combination of some function of r and some function of theta, and then substitute that in this equation and find out the relation between those functions. That exercise will not do in this class. If you see any book on elasticity, that exercise is given, and the detailed solution of phi is given in these two articles. Okay. So, how to find out this solution, that approach is given in the book, and further details of that solution, further detail of relation between different constants and everything, that is given in these two articles. So, those who are interested to get the insight into how the solution is obtained, for a general solution of this equation is obtained, you can please refer to this article. Now, the general solution of phi based on the exercise given in these two articles, the phi can have a general expression like this. So, this expression is a general solution of the biharmonic equation that just now we have seen in the previous slide. Now, please look at this expression. This is an infinite series. This is a general solution, but when we apply this method to a particular problem, we won't take all the terms. We'll take a finite number of terms from this general expression. We'll show you that. Now, here the approach will be like this. Approach very similar to the problem in Cartesian coordinate system. The first thing what we did is once the problem is described, once we have the problem description before us, the first step in the solution we did is we assume some expression of phi, okay, and in that case that expression was assumed as a polynomial. Now, here also the first step is assumption. We have to assume some expression of phi, but then here the phi is assumed, phi is assumed by taking some finite number of terms from this general expression. Okay. Now, for instance, suppose before actually we apply this to a more general problem, let us see a very let us slightly simplify the problem for the demonstration. Suppose we have a problem which is axisymmetric. Axisymmetric problem means the problem, the geometry, boundary conditions, loading, everything is symmetric with respect to an axis. For instance, in this case, if you take this, the entire problem, the geometry and all this loading is symmetric with respect to this axis. So, this is called axisymmetric axis, right. Similarly, if you take this problem, everything is symmetric with respect to an axis. If you have a loading something like this, for instance, all these everywhere are. When we say in an axisymmetric problem, it is just not the geometry, boundary conditions, loading, everything has to be symmetric with respect to this axis. In this case, it is a plane problem. In this case, the axisymmetric axis is the point is this, and the axis passing through this normal to this plane is the axisymmetric axis. Now, it may be applied to some external loading. For instance, it is applied to some loading like this, uniform pressure everywhere. So, these are some axisymmetric problem. Okay. Similarly, this is in this case this is your axisymmetric axis. This case the axisymmetric point is along is normal to this normal to the plane of this figure. Now, one important point to be noted here, we will come to that point shortly. If you recall, we discussed some time back when we actually describe different kinds of continuum, we define two such continuum. One is the connected domain or one is simply connected domain, and one is which are not simply connected domain, multiply connected domain. For instance, these are all simply connected domain, whereas this domain and this domain are multiply connected domain. And if you recall, at that time we made a statement, but we did not prove that. We made a statement that the compatibility condition and equilibrium, why we needed compatibility condition to have a unique displacement field, right? Because the displacements need to be compatible with each other. If the compatibility condition is not satisfied, then the solution may not be unique. So, compatibility condition helps us to arrive at a unique solution, right? A unique displacement field. At that point, we made a statement that this may not be guaranteed if the domain is not simply connected domain. Okay. We will shortly see through an example, through one of such example, if the domain is not simply connected, even the compatibility condition is satisfied, but the uniqueness in the displacement field is not guaranteed. It is a necessary condition, but not sufficient condition. Okay. Now, suppose we have to find a solution of a problem which is axisymmetric, right? Now, in an axisymmetric problem, we know that everything is symmetric with respect to an axis, and therefore, now as I just now discussed, we have to, when we start a solution, the first step is to get an approximation of phi, assume some phi. Now, when we assume some phi, it is an infinite series. We cannot deal with infinite number of terms. We have to get the finite number of terms, right? There we have to use some information about the problem. What are the information we have about the boundary condition? What are the information we have of the nature of the problem? By intuition, if we can assess some deformation or some deformation characteristic of the problem, that may also go in, that information may also go in while choosing phi. For instance, in this case, if our problem is axisymmetric problem, then all the term which is dependent on theta, for instance, this term depends on theta, 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 this term depends on theta. If the problem is axisymmetric, we can straight away remove this term, and we are left with only this term. Only 1, 2, 3, 4, only 4 constants we have, if the problem is axisymmetric problem. But if the problem is not axisymmetric problem, then we cannot make, we have to take the theta dependent term as well. Now, let us see, suppose now this is my phi, okay. We will also see that the some of the term also we may take for an axisymmetric problem, but very simplified case, we straight away we remove all the term associated, all the theta dependent term, and then take only this term. Okay. Now, let us see what happens next if we take only this term, right, and then what we have? We have a relation of sigma r, sigma theta, sigma r theta and phi. So, straight away we can find out, we can say take this. So, we can substitute this phi from this expression into this expression and get the expression for sigma r, sigma theta and sigma r theta. And if we do that exercise, we have an expression like this. Okay. Now, Here is an important point. One exercise that you have to do is check whether this phi, when we say this phi, satisfy biharmonic equation or not, whether this phi satisfy del 4 phi is equal to 0, whether this satisfied or not. Okay. You have to check this first. Okay. If you find that this phi satisfies this equation, then it is a valid stress function. So, from this phi we can obtain these stresses, and this whatever constants we have, this constant we can obtain this constant by applying the boundary conditions or the information about the problem that we have. Okay. But suppose your domain is this. Okay. Now, this we have a point here, and then this direction is r, this direction is r. Okay. And at this point r is equal to, at the axisymmetric point r is equal to 0. Okay. When we say that this is my potential, this is the stress function, and from this stress function we have an expression of stresses like this, this stress function valid over the entire domain, and therefore, the stress components that we have from this stress function, these stress components also valid over the entire domain. It has to be valid over the entire domain, isn't it? Now, but the problem is, if it has to be valid over the entire domain, and entire domain consists r is equal to 0 as well. The point r is equal to 0, also a point belongs to that domain. If this equation is valid over the domain, then this equation has to be valid at r is equal to 0 as well, because r is equal to 0 is a part of the domain. But now, look at, we have 1 by r square term here, and then we also have log r term here, right. Then if this equation has to be valid over the entire domain, then straight away we can say that this has to be 0. A1 has to be 0 and A3 has to be 0. So, this part becomes 0, this part becomes 0, A3 is 0, again this part is 0, this part is 0, again A3 is 0, right. Now, if they are 0, because the domain contains, because otherwise that the continuity is not satisfied, we have an infinite, the 1 by r square is not valid stress field at r is equal to 0. Then if we substitute all the term is equal to 0, then what we are left? What are left? Then sigma r becomes 2a2 and sigma theta becomes 2a2 and sigma r theta becomes 0. This is a very important observation. Now, this observation says that if you take this as your stress function and your domain is this simply connected domain, then this stress function can give you only constant stress field. Sigma r and sigma theta both are same. Sigma r is equal to sigma theta is equal to 2a2 in this case. Okay. Now, let us, this information we get from this. Okay. Let us go beyond this information. Let us see further, let us go further deeper and then see what other information this gives us. Now, but interestingly, if your domain is different, if your domain is like this, you take it here. Now, if the domain is not like this, if the domain is like this, then r is equal to 0, this is r is equal to 0, and r is equal to 0 does not belong to this domain, and therefore, this equation is valid over the domain, but since r is equal to 0 does not belong to the domain, and therefore, this term and this term will not give you invalid stress field, right, because then in that case all these terms are valid term. All these terms are, we can keep 1 by r square term and log r term if the domain is this. So, this is simply connected domain, but if the domain is not simply connected domain, then we can have the entire thing, which is, and this is not constant stress field. But if we start with, if we take this as our potential, this as our potential, and our domain is simply connected, this as our stress function, and the domain is simply connected domain, then we can only arrive at constant stress field with this stress function. But if the domain is not simply connected, then this can give us a different stress field. Now, so once we have these stresses for either this domain or this domain, consider it is a plane stress problem, and then we know the stress strain relation for plane stress, substitute all these stresses into that relation, get the strain component, and once we have the strain component, integrate that strain component to get the displacement. And if we do that exercise, then this will be the displacement field. This is for radial displacement, and this is for tangential, this is for u r, and this is for u theta. Okay. Now, one more thing. Now, consider two cases, case 1 or case 1. Your domain is this. If your case 1 domain is this, A3 and A1 all are 0. Okay. Now, in this expression, then naturally this term becomes 0, A1 term becomes 0, this term becomes 0, and then this term becomes 0. Okay. We are left with only this term. Okay. Now, if we substitute some boundary conditions and all, we can also show that this term will also be 0. The constant term will also, this bar A and B, the constant term will also be 0. We can choose the boundary condition accordingly. So, the strain component only has this term, right. The displacement component only have this term, and the displacement component only have this term. There is no theta term here. Okay. For case 1. Now, what happened for case 2? Case 2, suppose this is case 2. Case 2. Case 2, we really do not have to make A1 and A3 0, because having this term in this stress field does not violate the definition of continuous stress field, or the stress field is still valid, because r is equal to 0 does not belong to this. Now, so A3 and A1 are not 0 if in the case of case 2. We can assume some boundary conditions and make at the most, suppose this part becomes 0, okay, or this part have some values, okay, or 0 this part, this part. But rest of the things A1, A3, A2 all are non-zero. We cannot make them 0 by just the condition that we applied for the first case. Now, you see, look at this U3, it contains theta. Okay. Now, theta could be anything. If you recall that expression, the general solution, the expression is obtained as theta could be, say, theta may be theta, or maybe theta 1, maybe theta 1 plus 2 pi, or maybe theta 1 plus 2 n pi, could be anything. Theta could be anything, right. What it means is, suppose you start with this is your theta, you take a point, this is theta, and then again you come to this point, your theta becomes theta plus 2 phi. Again you come to this point, the same point, now the theta becomes theta plus 4 pi. Now, what is for the same point can be expressed by different theta, right. But if you substitute different theta here, sin theta, having sin theta and cos theta term, for the same point, if you substitute theta plus theta plus 2n pi, these will remain same, this term will remain, this will not be different. But what will happen is, this term 4r theta, this term will be different. For instance, when your theta is, so u theta becomes 4r theta by a3, sorry, you write u theta is equal to 4r theta by e into a3 for theta. For theta plus 2 phi, u theta becomes 8r theta, sorry, theta becomes 4r theta plus 2 pi by e into a3. For theta is equal to theta plus 4 pi, u theta will be something else. But theta plus 2 pi, theta plus 4 pi, they all correspond to same point, they all refer to the same point, isn't it? It shows that for the same point we have different u theta, means u theta is not unique, we have different values of u theta for the same point, right. But that problem we did not have in the case of the first domain, because the domain was such that we can straight away make a1 and a3 0, a1 and a3 0. But for the second problem, we cannot make a1 and a3 0, and this a3, this term associated with a3 in u theta term, this will create a problem. Problem in the sense, this causes the displacement field, this imposes non-uniqueness in the displacement field. That is the reason why, you see, the stress function that we started with, that stress function satisfies biharmonic equation, right. And what is biharmonic equation? It is as if you are starting biharmonic equation, and then if it satisfies biharmonic equation, means it satisfies the equilibrium and compatibility both. Even after that, even after satisfying the compatibility equation, for the second case where your domain is not simply connected, we have seen that we may have non-unique displacement field, but in the first case displacement field was unique. That was the reason at that time we mentioned that it is a necessary condition, but not sufficient condition. It may not be guaranteed. We will come to this point again when we discuss the complex variable approach to solve different problems. Okay. So, now, so what we do is we stop here today. Next class we will start with this slide, the general expression, take up some example and then see how that example can be, how the stress field and the displacement field can be obtained by stress function method. But our the starting point will be this expression, this general expression from phi. From this general expression, we take some finite number of term and then find out the solution, find out the values of different constants. Okay, I will stop here today. See you in the next class. Thank you.